Uh, in electrical properties, we can characterize the materials like metal, semiconductor, and insulator. And the metal, in metal case, electric currents. When you apply the electric currents, and electric charges flows very well in materials. And a semiconductor depends on the conditions. And when we increase the temperature or make a bias, then electrons can transport in some cases or not, and it is a semiconductor. And insulator is that in natural conditions, in room temperature, for example, room temperature without bias, then it is electric currents cannot flow in the materials. And here it is a metal case, and the energy band. There are two energy bands. One is that valence band. Valence band is the core electrons, and the electron are localized in the near the ions. And the conduction electrons in an energy band that itinerant electrons, and electrons can flow. And here the Fermi energy will define the Fermi energy later. And Fermi energy is the in physical definition of Fermi energy is the zero temperature chemical potential. And in zero temperature, Fermi energy is the energy that highest the energy level of electrons. And here in the conduction electrons and the valence electrons, if there is an energy band gap, here is the prohibited region that energy in this energy band gap, there is no probability that reside in between the energy band gap. Therefore, only the higher energy and the lower energy can exist. And here at room temperature, and the valence band, red one, is fully occupied, and the conduction band is empty in insulator. But in high temperature, the valence electron should overcome the energy band gap energy to flow the conduction band region. Therefore, and in insulator, the energy band gap is enough to large comparing to the thermal excitation energy, and therefore there is no population for flowing the electrons in the conduction band side. And rather than the semiconductor, is that energy band gap region is comparable to the thermal excitation energy, and thermal excitation can overcome the energy band gap level. Therefore, the valence electron can go to the can excite to the conduction band side, and therefore, in some cases, at high temperature, or by applying the bias, and the valence electron can flow to the conduction electrons. In metals, there is no energy band gap, and therefore the valence electron, there is no energy difference between the valence electron and conduction electrons. There is no energy needed. There is no energy needed to flow the conduction electrons. Therefore, metal always easy to flow the charge currents in materials. Then, what's the origin of this energy band gap? And it is this question. And as I said before, the energy, and here the Fermi energy. Fermi energy is the highest energy level that room at zero temperature. And metal, there is no energy band gap and the band overlap between the conduction band and valence electron. And also semiconductor or the insulator, there should have the energy band gap like this. We call it as a delta. In the same, there are the other case, there are same metal case is that the conduction electron and valence electrons has this kind of, there is no energy band gap, but energy band gap crossing, and it is metal. We call it as the same metal. It is the semiconductor or the insulator. Then what is the semiconductor and insulator? And the energy band gap is lower than the thermal fluctuation energy. It is a semiconductor. The thermal activation energy can overcome the energy band gap energy, but the energy band gap is largely enough to the thermal excitation energy, then it is an insulator. When I say in conclude, indeed, the origin of the energy band gap is a Bragg reflection of the electronic wave function. And the origin of energy gap is the Bragg reflection of electronic wave function, electron wave at the zone boundaries. And as I said, there is a periodic boundary condition, and we call there is a Brillouin zone in momentum space, and also the periodic lattices makes the for example, when you see that it is a Brillouin zone, the electronic wave is in real space. In real space, there is a periodic. In the electron wave, there is a wave function. Anyway, let's assume that this is an electronic wave, and also this point and this point is identical, because in the reciprocal lattice vector G, then this point and this point is identical, because it is a unicell, and the unicell is repeating in real space, and therefore in momentum space can be reduced. And also in momentum space there is minus pi of a, and pi of a, it is when there is lattice spacing a, then here the first Brillouin zone can be reduced, and also it is a first Brillouin zone in momentum space. And therefore then when it is entered, it is exceed of this region, but when in this side, it is here interfere with each other. The electron and this region and this region are identical. It is when it can be have the reflection, transmission or the reflection, and transmitted electron wave is the same as the entrance of electrons here. Therefore, there is a interaction between the transmitted or the reflected one, and we can think about that it makes a standing wave of the solid in the reciprocal space. We call it is a Bragg reflection. At the zone boundary, there is a Bragg reflection because this point has a periodic, and it is the same within this case. Therefore, and at the first Brillouin zone, there is a Bragg reflection of the electron wave can interfere with each other, and it is origin of the energy band gap. And here we can define that the first Brillouin zone, is that K is the plus minus pi of A, and suppose that the Bragg reflections of a wave function makes standing wave makes standing waves. Then here it is. Then there is a negative potential. There is a periodic lattices. It is ions, periodic ions, and periodic ions makes the negative potential, and the spacing between ions is A. Then here the electrons flows from the right side to the left side. Let's suppose that wave function plus wave function is a right traveling wave, and the minus wave function traveling to the left side. Then the amplitude of the traveling wave is the scale of the wave function, and the right traveling wave and left traveling waves can interfere with each other. Then let's suppose that the wave function for right traveling wave is that cosine function exponential I pi x over a plus exponential minus I pi x over a. It is a 2 cosine function pi x over a. It is a cosine function, and the minus wave is that exponential I pi x over a minus exponential minus I pi x over a. It is 2i sine function pi x over a. Then the charge density is the square of the wave function. Psi plus square is that right traveling wave, and it is proportional to the square cosine pi x over a. And the left side wave function is that minus, it is proportional to the sine square pi x over a. Here we assume that the potential energy is that cosine function 2 pi x over a. It is a periodic potential function, and charge density can be represented like this. Then there is an energy difference between the right traveling wave and the left traveling wave, and let's consider for the energy difference. Between psi plus and psi minus. Then the energy difference, we call it is energy band gap, and also let's define that from 0 to 1 dx, and the potential, and also psi plus square minus psi minus square. It is energy difference between the two traveling waves. Then let's calculate the energy, the wave function from 0 to 1 dx, and the psi plus square. Because psi plus square can be write down like this, and from the lattice spacing 0 to a dx, and the amplitude square cosine square pi x over a. Then we know the formula, cosine formula, that cosine 2x equal to cosine square x minus sine square x equal to 2 cosine square x minus 1. Therefore, cosine square x is that 1/2, 1 plus cosine 2x. Then when we use this formula, then the above integration is that a square over 2 integral 0 to a dx, and 1 plus cosine 2 pi x over a. Then integral of cosine, it becomes the sine, then the integrand x equal to a on 0, it is 2 pi and 0. Therefore, this term is cancelled. This term is 0 at the edge of from the integral in between 0 to a. Therefore, it is that a square over 2 and the integral a, it should be 1 because it is a normalization of this function, and therefore the amplitude is that square root 2 over a. Therefore, this psi is that from when we consider the normalization of the wave function, it is 2 over a cosine pi x over a, and the psi minus is that in the similar way, and the 2 over a sine pi x over a. Therefore, the energy difference, energy band gap, can be calculated, and also because it is a square, and 2 over a integral dx, then potential is that the v cosine 2 pi x over a, and also psi plus a square is that cosine square pi x over a minus sine square pi x over a. Then it is that here it is the cosine 2 pi over a. Therefore, it is that 2 over a integral dx v cosine square 2 pi x over a. Then it is that from the same formula, v over a integral from 0 to a dx 1 plus cosine 4 pi x over a. Because this cosine term also 0, because integral sine from 0 to a is equal to 0. Therefore, it is a v over a, and multiplying a should have the v. Therefore, the energy gap, energy difference between the two traveling wave is the energy band gap is same with the potential. And therefore, the Bragg reflection between two traveling waves and the periodic in periodic potential, the energy band gap is identical to the potential. Yeah.